guys, welcome to your first lesson of Chapter 8 on modeling inverse and joint variation. We've talked quite a little bit about modeling direct variation back in Chapter 2. In Chapter 2 we were dealing with this idea that x and y vary directly, and so you had something in the form y equals ax, where effectively a was what we called our constant of variation, and x and y varied directly. This chapter we're going to talk a little bit more about this idea of inverse variation, and then we'll talk about joint variation where you have more than one variation going on at once. Okay? All right, so a couple things. First of all, inverse variation says two variables x and y show an inverse variation if they're related as follows, where y equals a over x, and as long as a is not equal to 0. Now, obviously, a can't be equal to 0 because this becomes y equals 0 over x, which is simply 0, and so it doesn't matter what the value of x is. Also, we know that this function is only defined so long that x is not equal to 0, because if x is equal to 0, you get something over 0, which is undefined. The constant of variation is that non-zero constant a in the variation equation. All right, now joint variation is when a quantity varies directly with the product of two or more other quantities. All right, so it's again a direct variation where we're varying with two or more other quantities. So we might have an x, a y, and a z now. So again, throwing a third variable at you, but not too terribly difficult when we get to that piece. Okay? All right, so let's take a look at a few examples here, and let's see if we can't make some sense out of this idea of inverse variation. All right? We're going to start off with inverse variation. Again, inverse variation, two variables, x and y, show an inverse variation if they are related as follows. Again, y equals a over x, where again, to be inverse, again, inverse says that x is being moved to the bottom. All right, we know that the function inverse, the idea of inverse, says -1, and so if two things are inversely related, that says that x gets moved to the denominator. All right, so varying directly is this. Varying inversely is this. So this is direct. This is inverse. All right? They look almost identical, but the big thing is where is the x? Is the x in the top? If it's in the top, it's direct. If it's in the bottom, it's inverse. All right? The constant a is the constant with constant variation, and y is said to vary inversely with x. All right? So, classify direct variation and inverse variation. It says tell whether x and y show direct or inverse variation or neither. So, in this case, it says y divided by 9 is equal to x. Again, to be in this form, it must say y equals. So, if I multiply both sides by 9, I get y equals, and instead of x9, we're going to say 9x. And so, obviously, this is a direct variation. All right. Whereas this one, if I divide both sides by x to make it say x or y equals, okay, this cancels out, and I get y equals 3 divided by x, and so that is an inverse variation. All right, so why don't you guys try a couple? Pretty straightforward. Go ahead and try a few, and we'll be right back with a solution. All right, so in the next example, it already says y equals, but it doesn't say 2 times x or x over 2, for example, or I'm sorry, 2 over x. This is just a linear equation with a y-intercept of 2. These two do not vary inversely or directly. This one is a neither. Okay, because again, it has to be the product of 2 and x or the quotient of 2 and x. For this one, divide both sides by x, and you get y is equal to 5 divided by x. Well, 5 divided by x is an inverse. That's an inverse variation. And then for the next one, again, it looks like it's inverse because of the fraction, but if I multiply both sides by 2.6 to make it say y equals, it now says y equals 2.6x, and so this is a direct variation. All right? So let's try to write one of these one of these inverse variation equations. It tells me that the two variables x and y vary inversely. When y equals 3, x equals 6, write an equation that relates x and y, and then find y when x equals -9. So this last statement, we'll deal with that in just a few minutes here. Again, this part of it is coming up for the latter part of this problem. So we're going to leave that on the side burner for right now. Let's deal with the other piece. By definition, since they vary inversely, y equals a over x, we're going to substitute in the values for x and y we're given. So 3 is equal to a divided by 6. Multiply both sides by 6, and you get a is equal to 18. So my inverse variation equation is then y equals 18 divided by x. Okay? So then it says when x equals negative 9, well then y is going to be equal to 18. Sorry, I almost wrote negative 18. 18 divided by negative 9, because again it's y over x, or I'm sorry, a over x. So it's 18 divided by negative 9, which is negative 2. So the ordered pair negative 9, negative 2 is also a piece of that inverse variation. Okay? All right, why don't you guys try the checkpoint? Again, we'll be right back with a solution. Make sure you're trying this first on your own, so pause your video and give it a shot. All right, so if these two things vary inversely, again, they vary inversely, so we're going to follow the form y equals a over x. We're then going to plug in the stuff we're given, so 4.4 is equal to a divided by x, which is 5. So we're going to multiply both sides of this thing by 5. Sorry, that's supposed to be a 5 here. All right, these are going to cancel, and I'm going to get a is equal to, I get 22 here. All right, so once I know that a is equal to 22, my my inverse variation equation becomes y equals 22 over x. All right, then it says write an equation. Okay, we've already written an equation. I'm sorry, find y when x equals 8. So y equals 22 over x, which is 8. And 22 divided by 8 comes out to, well, these are both even, so this goes in here 4 times and 11 times. So y equals 11/4. You can also give that as a decimal value, which is 2.75. All right? All right, so let's try to check a set of data to see if it does model inverse variation. So again, to model inverse variation, we can go back to this idea of saying, look, if these two things vary inversely, and it's saying write a model that gives n as a function of m. So n would have to equal a divided by m if they are to vary inversely. Well, this is a constant, and that has to stay the same. So if these two things vary inversely, then I should be able to multiply both sides by m, and a will be equal to the product of m times n. Now, if this is a constant quantity, the product of m and n, okay, then that says that this is an inverse variation. So let's take the product of the m, the n term, 5 times 45, which becomes 225. Let's do this one, 10 times 22.5, hey, guess what, 225. What do you suppose 15 times 15 is? Yeah, that's right, 225. You guys getting a pattern here? 225, 225. So every one of them, m times n, is equal to 225. So since the product of each one of these is 225, the data does model inverse variation. Okay, the data does show, that's grammar, does show inverse variation. Model relating m and n then becomes m times n equals 225, and if I want to write n as a function of m, I would divide both sides by m, and I get n is equal to 225 over m. All right? And so the value of n when m equals 45 becomes n equals 225 over 45, and 225 divided by 45 comes out to 5. All right? Top of the next page then, you guessed it, checkpoint. Okay, let's give it a shot. All right, so again, if x and y vary inversely, then y equals ax. And so if I multiply both sides by x, my constant of variation will be the product of x and y. And again, if that shows a constant value, then this is a inverse variation. So 2 times 18 is 36. 9 times 4 is 36. 6 times 6 is 36. You guessed it. 8 times 4.5. Yeah, everything's coming out to 36 here. So the product is 36 every time. So x times y equals 36 can be written as an inverse variation by simply saying y equals 36 divided by x. So there's my inverse variation equation. And I don't think this one, no, it doesn't give us a value of x to try. All right, so we've got our model, and we're in good shape. All right? All right, let's talk a little bit about joint variation. Again, joint variation is exactly what it sounds like. It joins a couple of variations. So joint variation occurs when a quantity varies directly with the product of more than one, 2 or more in this case, quantities. All right. In the equation below, a is a non-zero constant, so z is equal to a times x times y. And so now we're going to say that z varies jointly with x and y. So, you know, x increases, y decreases, and whatever. You know, you can change the values of x and y, but again, you still have your constant of variation, but now you're varying with two quantities, and so that's why we call it joint variation. All right? So let's go ahead and try to write a joint variation equation. Obviously, in this case, we're going to have a little bit more information because there are three variables and one constant. It says the variable z varies jointly with x and y. So that tells me, by definition, z is equal to, sorry about that, tells me that z is equal to axy. All right? It also tells us that z equals negative 84 when x equals negative 4 and y equals 3. So write an equation that relates x, y, and z, then find z when x is 5 and y is 2. So the first thing we have to do is we have to solve this thing for a. So negative 4 times 3 becomes negative 12. Divide both sides by negative 12. And I get that a is equal, I'm sorry, this is negative 12 here. So negative 12 equals negative 84. Now divide by negative 12. And you end up getting that a is equal to 7. All right? So the joint variation equation is z equals 7 times x times y. And then it says calculate z when x equals 5 and y equals 2. So this is 7 times 5 times 2. 7 times 5 is 35, times 2 is 70. And so z equals 70. All right? Okay, let's go ahead and compare some different types of variation then. And let's see if we can write some equations, because now we're going to start kind of mixing and matching a little bit. The first one's pretty straightforward, and then they get a little bit more complicated. It says m varies jointly with n, p, and q. So m varies jointly, so that means that there's a constant of variation in here, with n, p, and q. N, p, and q. So kind of a goofy equation, but m equals a times n times p times q, where a is my constant of variation. R varies inversely with s. Okay, r equals a over s. All right. X varies inversely with the cube of y. All right, so let's deal with that first. X varies inversely. Okay, so that's a over, right? And because it's inversely, we have a over, and then with the cube of y, so now we're going to make it y cubed. So this is x equals a over y cubed. Let's see if I can clean that up a little bit for you, okay? All right, k varies jointly with x and y. All right, so k varies jointly with x and y. I'm going to move this over because I don't think I quite have enough room here. All right, so first of all, we vary jointly with x and y. So a, x, and y. That would be the first part of it. And inversely with m. All right, so if I ignore this piece over here, okay, just kind of ignore that part of it for just a second, and say, all right, let's just forget that's even there. K varies, forget about this, k varies inversely with m, says k equals a over m. All right? So because it varies jointly with x and y and inversely with m, x and y are on top, m is on the bottom. All right? So we get a x, y all over m. All right, t varies directly with u and inversely with w. All right, so if t varies directly with u, that's t equals a over u. And, I'm sorry, that's not correct. It'd be a times u. And if it's inversely with w, t would equal a over w. So the u goes on top because it's direct. The w goes on the bottom since it's inverse. And so t is equal to a u all over w. All right, so let's see if we can try a couple checkpoint problems here. And this should finish up the lesson. Go ahead and give these a shot. We'll be right back with a solution. All right, so z varies jointly with x and y. So we get z is equal to a xy. Also, z equals negative 44. This is my a. X is 4. Y is negative 1. So write an equation that relates x, y, and z, and then find z. So we first have to find our a value. This is negative 4, so we're going to divide by negative 4. And I get a is equal to 11. So my joint variation equation becomes z equals 11xy. Now, we're going to get the values of z, x, and y. Of x and y, and we have to solve for z. So z equals 11 times the x we're given, which is 6, times the y we're given, which is 3. 6 times 3 is 18, and 18 times 11 comes out to 198. All right, and so z is 198 when x is 6 and y is 3. All right, write an equation for the relationship. X varies jointly with y and z and inversely with the square of t. So x varies jointly with y and z, but inversely with the square of t. All right, so inversely says the square of t goes on the bottom. All right, jointly says that x and y are on top with my constant of variation, which is always a. All right, so that's what we can do with that particular problem. So that is joint and inverse variation, and that concludes lesson 8.1.